cosmic storm. Floating on whimsical wavelengths is the norm. Dancing through the stars, chasing spectrums of light. Riding the waves that are just out of sight.
Welcome back to Whimsical Wavelengths. This time we're digging deep into the bedrock of discovery. This episode is where geology meets algorithms, and the motherlode is just a model away. We're using computers to crunch the crust, letting machine learning mine the patterns hidden in the data. This episode is loaded with knowledge that's anything but artificial, even though the intelligence is... and the puns are terrible. So machine learning, and the topic of this episode, is a bit outside of my wheelhouse. So I have a guest, and no, not just any guest, a coworker from my alter ego. Yes. So far, we've had a couple of guests that use scientific results as the basis for their career outside of academic institutions. Let's add one more. Before I get further into the introduction, many months ago I had asked for someone from my company I work for, Computational Geosciences, to come on the podcast and talk about machine learning and its applications in mineral exploration. It got delayed due to getting some results and a shuffle of personnel and more normal real-life stuff. So this conversation is months in the making. It's also all about science. Lots of science takes place within the corporate world. This here is a chance to look at one aspect. It isn't all about laboratories and classrooms, it's also about boardrooms. There's lots of ways to have a career in science. Now, let's set it up. We've been mining minerals from the ground for thousands of years. All the deposits close to the surface and near people have been mined. They're gone. So the deposits we have left are either in remote places or many hundreds of meters under the ground. That means they're harder to find and harder to extract those shiny resources needed for our modern world. Today we also have a lot of data. Satellite imagery, topography, LiDAR, geophysical surveys like gravity. See episode 12 for an explanation on Bouguer gravity. Or magnetics. There's so much more. You'll see that sites that have a lot of data typically also have a lot of drilling. This is where they've cored into the earth to take samples deep within. I think this is a good detour. Drilling, especially when the area is not near a road, it's quite an endeavor. The drill rig is something that needs to be moved by heavy machinery or a large truck. Flying it into site is not simple in many areas. They take a lot of fuel, a crew of at least 4 people to run 24/7. Each hole, after all is said and done, costs well over $100,000. And what do you get? Cylindrical sections of rock for the entire drill hole. Being approximately 6 centimeters in diameter, the information brought up is expensive. It's the only way to directly observe what we infer from the surface. Is there mineralization there? Will it be there next? Mine. A lot is done with that core of rock. Geochemistry, rock type, structures like fractures are all written down and described. The point is you don't want to miss with the drill. Drilling is expensive. Whatever increases your success rate and costs less than drilling is useful. Enter mineral prospectivity. Geophysics, drilling, remote sensing. With all that data, it is still hard to find the shiny stuff. And as said, drilling is expensive. To help combat this, we turn to machine learning and artificial intelligence to find patterns in the data humans may miss. To get enlightenment on this, a data scientist and my coworker from the best place to work on Earth. And no, I'm not just saying that. He joins the show. Here with us today is a data scientist with Computational Geosciences Inc. He got his Bachelor's of Science from the University of Leeds, a Master's from Western University, and then transitioned to industry using his degrees in geophysics and continues to use science to solve problems. Please welcome Frederick Jackson to Whimsical Wavelengths.
Hi, Jeff. Thank you for having me. I'm a big fan.
Oh, that's nice. And no, I didn't pay him to say that. For those that are long-time listeners, the reason why I made that joke is because the listener question at the end of episode 11 about the Spinosaurus controversies actually came from Frederick here. A trick up my sleeve to make sure at least one more person listened to the episode. But more broadly, how does your interest in dinosaurs and other science avenues fit into your path to where you are today as a data scientist?
Yeah, and by the way, I follow paleontology quite closely, and there was actually, I don't know when you'll release this episode, but at the time of recording, there was a paper released yesterday, I believe, on describing a new Spinosaurus species, which the name I forget, but it's quite a similar species to Spinosaurus aegypticus, which you would have discussed, but it has this really cool head crest on the top of its head, probably for display purposes, and it's a very interesting new discovery. So that's something your listeners might be interested to hear. Yeah, to answer your question, I think, when I was a kid, I thought dinosaurs were big and impressive and cool. And as an adult, I actually think what makes them so interesting is the kind of mystery involved in understanding them, because we can't go back in time to see what they looked like. We can't clone them and bring them back to life like in the movies. So instead there's been these kind of centuries of detective work where we're only just starting to scratch the surface of what they actually looked like and behaved like. And I think there are a lot of parallels between that and what we do at CGI. We're doing geological and geophysical characterization. We're building methods that uncover the mysteries of the Earth in the same way that paleontology uncovers the mysteries of ancient life. And I think both they require a certain imagination combined with evidence, like real evidence.
So what you're saying is that your job today kind of marries some of the great things that you've always wanted to study, but provides a practical aspect to it moving forward, kind of like the industry and the like.
Yeah, exactly. I think there's a common thread of, I think all scientists have the kind of thirst for discovery in a way.
Yeah, and that's like a perfect segue to the next question, because before we kind of pivot towards the technical part, the process of conducting science is just as important as the results sometimes, and that's what we're talking about. So here on Whimsical Wavelengths, we've covered papers that have come from universities and museums mostly. As far as like a direct paper from industry, like we've had some industry types on, but they didn't bring a paper they wrote for industry. It was usually it was either a topic or from their PhD thesis or something like that. And that's not a problem, but this is pretty sure the first one directly from industry. Peer review is the same though, but there are some differences. For us, because I'm also employed at Computational Geosciences, what's the biggest difference between industry science and kind of like what you would do is like just strictly for academics?
Yeah, I've thought about this a lot actually, because I obviously had a brief period in academia and published some papers and then took some time off from the research side, and now I'm kind of back in the area of publishing again. I think the biggest difference is kind of the consequence of actually being wrong with your results. I think in academia, if it doesn't quite work, then you might get your null result or whatever, and have to rethink your project. But life goes on. Whereas if we tell a client to dig somewhere and there's nothing there, then that's a very expensive mistake for a client. So you're balancing this like scientific discovery process using the science to find things with the kind of risk management side of things, like generating models which are maybe slightly more cautious in terms of their predictive capabilities than otherwise. So I think there's it's the risk management side of things that's a bit different.
Yeah, one of the other things I want to kind of poke at here is peer review is the same. So once something gets through peer review, it doesn't really matter where it came from too much. Again, it's always one paper, so if it's industry, you should probably see it in an academic journal from an academic point of view eventually. You can't always just do one, but there's also there's a different emphasis on publishing in industry, isn't there? Like, you're not just in the pursuit of knowledge, you only publish kind of what you want to, right?
Yeah, there's always like a financial incentive to it, I feel like. And in fact, a lot of people don't publish, right? Like a lot of companies will keep their trade secrets because that's their moneymaker. I don't know. I think I disagree with that. I think by publishing and discussing what we do at conferences and things, I think we're showing people that what we do is solid and backed by science and open to public scrutiny. I think that kind of transparency builds a certain trust in what we do, and I think if we can prove what we do in areas like this paper we're studying some areas in Australia, I think if we can prove that it works there, then people trust it when we suggest using it in other areas where people haven't looked before.
All right, so the paper we're actually about to dive into with this Australia data is formulating gold prospectivity mapping as a constrained learning problem. It was submitted and accepted to the Society of Exploration Geophysics for a meeting last year for the Applied Geoscience and Energy. Is there anything that you need to add to from the preamble that was part of the intro, or like what problem is this trying to address?
Yeah, and by the way, quick update. It should be published this month. Again, I'm not sure when you're releasing this, but it should be published in February in the SEG library. So it should be accessible by the time this comes out, I would imagine. But yes, so no, I think you did a good job. I think the motivation really is how complicated mineral systems are. They can occur on these tiny little centimeter length scales, and they're formed by incredibly complex and poorly understood geological causation. And traditional exploration, I think, is very good at filling in the gaps between your knowns, but it's the extrapolating which is the difficult part, and the kind of the thing that AI prospectivity is attempting to approach. What we're trying to do is to build a model which can do that, can extrapolate from a well-known area into an area that it doesn't know about at all, whilst also managing that risk. Again, it comes back to managing risk, managing the risk of the model hallucinating or getting confused when we move away from the safe areas, I guess.
Okay, so let's expand some of those ideas out right here, I guess. Prospectivity and machine learning is essentially, it's the machine learning side of it that you're talking about, the networking. So the average person listening to this has heard of large language models like ChatGPT, and that they're trained by scraping art and music and writing from the internet in an effort to learn to respond more human-like and give information and answers. So leaving the pitfalls and issues with that process aside for now, so how does that work in principle here? Because that's what you're talking about, of being able to extrapolate from a well-known area to a less known area. I'm assuming you're having to train on data, very similarly to LLMs. So how is it different, and how is that kind of all taking place? Like what?
Yeah, the concept is very similar. So as you say, ChatGPT has been, it's learned how humans communicate via its training data, which is the internet, and it's able to extrapolate its responses to things it hasn't heard before. And what we're doing is we're building an algorithm which has, in principle, if we've done our job, it's learned how mineral systems form via the geological training data, and it's extrapolating those, I guess, like formation mechanisms to areas that it hasn't seen before in the same way ChatGPT has. So that's the similarity. I think the difference is the amount of data. I think ChatGPT obviously had the whole internet to scrape from. We don't quite have that privilege. So ChatGPT achieves like insanely creepy level of human. I don't know if you ever like speak to it. Do you ever do like a back and forth conversation with it? It's creepy how
and
how
full
realistic it is.
disclosure, I often give it podcast stuff and ask it to like critique my stuff, and sometimes the stuff it gives me back, you're like, oh.
Yeah, we don't quite have that level of training data. So again, it's back to that risk management thing. It's about how to make it work with the limited data that we have in the geological world, because drilling is expensive in geological exploration. Geochemical sampling is often quite sparse. So it's about all those kind of limitations.
Yeah, so maybe we'll take a quick aside there. Do you happen to know, roughly speaking, how much a drill hole costs?
I actually have no idea. No.
Oh, okay. Well, I guess for the listener, it's usually in the many hundreds of thousands of dollars, depending on how many you're going to get done. If you're just going to go do one drill hole, it's like $1 million because you have to pay to get everybody on site. But then it's usually somewhere between $200,000 to $300,000 per drill hole.
I guess the depth as well depends on the depth.
Yeah, it depends on the depth. It depends on a lot of things. So if you're going to go really deep, then it's almost $1 million per drill hole. Or if you're going to do geothermal, because of the size of the drill hole, it'll be more expensive. But the point is, being able to de-risk those drill holes is really important for the industry. So as you were saying, you don't have the same amounts of data as a lot of these LLMs, because you're dealing with an area which we only have what information we have is what we can measure. So the paper uses data that is either already public or you've received some kind of special permission to be able to publish it, right? So What is that data that you're using to train in this paper, which is on Australia, and build that geological equivalent to ChatGPT?
Yeah, so we're focusing on Western Australia, and Australia is very good at releasing their data for public use. There's a website called Geoscience Australia that publishes it merges and makes available a lot of exploration data, and they have essentially geophysics for all of Western Australia, which is absolutely ideal for a test project like this. So we went on Geoscience Australia. We assembled what we call a data cube, which is just a fancy name for a big folder of data. But we assembled, I think, something like 15 different data layers of public data from the Yilgarn Craton, which is an area of Western Australia, and that includes potential fields data, which is your magnetics and gravity data, the images into the subsurface. We have radiometrics, we have satellite imagery, and then we have the labels, which are our geochemical samples, and potentially the most important part of the whole puzzle. And the idea is to build up an analog to doing this on a more kind of brownfield level, I guess, like the kind of data that a client might potentially have at a kind of exploration target.
Okay, only because I know the words, and I'm going to try to expand them out here a little bit. When we deal with, I guess, potential fields, we're talking about someone's gone around and measured the Earth's magnetic field or gravitational field over a wide area, and you're taking that map and derivatives of that map as some of your data, right?
Yeah, exactly.
And for those that are not in the industry, brownfields means like you've had enough time to collect a lot of different data. You know that there's something under the ground and you're moving towards hopefully opening a mine. In a lot of cases, when we're looking for minerals, we call it green fields when we don't have a lot of data and you've maybe got one or two drill holes kind of idea. You're still trying to suss out whether or not there's anything of economic worth underneath the ground. Whereas brownfields, you're starting to move towards a mine. That doesn't mean you'll get there, but that's where you're moving to. So you have a lot of data, or at least a lot of data in the sense of geology, and data sets that I guess you can use for prospectivity. That summed it up pretty good. Did I miss anything?
No, yeah, perfect. And sorry, I'm using my I'm used to presenting this at conferences and things where the terminology is more known.
Yeah, but you're also talking to me, a coworker, who is going to understand what you say kind of instantaneously instead of for everyone who's listening somewhere else. I mean, don't be afraid to get nerdy, my friend. I mean, we all love maps, or at least we do. So I guess the next part of the conversation comes back to the geochem that you were just saying, the idea of we've already talked about the different data layers. But the data layers isn't really what you're training on, right? That's just giving the information for it to make pattern recognition with geologic layers or geologic targets versus what LLMs do with words, right? Mm-hmm. So you need to give it something, and you call that the labels.
Yeah. So in machine learning, you classify your data into features and labels. So features are the kind of wide area, extensive geophysics in this case, or remote sensing, and labels are the actual ground truth. So the concept of machine learning is that you're building this kind of causative link between your labels and your features. So the features are the observable thing which explain the existence of the labels. So in this case, the ground truth from the drilling is the labels, and the geophysics is the thing which is kind of explaining the reason for the labels being what they are.
Okay, just out of curiosity, there must be some pitfalls to this type of approach as well, right? Like in my own head, I come up with the simple thing is that if you're using ground geochemistry, something could have changed for the lack of obviously we wouldn't use this necessarily, but glaciers or rivers or flash floods can move things downstream and modify what we see. So is that a concern here? Is things that modify either humans or natural events that modify the subsurface? Is it a case of garbage in, garbage out?
Yeah, absolutely. That's the big caveat of all AI is the garbage in, garbage out thing. And geochemical sampling is especially prone to that human or instrument error or transported samples, like you were saying. And when you're building that causative link I mentioned, then that can obviously throw off your entire model. So yeah, garbage in, garbage out for sure. I mean, again, it comes back to that risk management thing, building these for real world applications. And that kind of prompted our approach that we present in this paper. Actually, it's a nice lead into that because we don't actually care in our approach about the exact like granular noise of a geochemical sample. We're kind of more looking at the bigger picture, the proximity to the kind of high grade like hits rather than the misses. So it's more resilient to that garbage because we're kind of building this sort of probability model based on the bigger picture rather than the kind of individual samples.
Okay, and that's what is new and novel with the paper, or is that specifically?
Yes, exactly.
I think we've kind of skipped over one part of this. So I've kind of waved a magic wand and said it's machine learning. We haven't really described what machine learning is.
Yeah, well, machine learning is kind of building that kind of causative link that I mentioned between some kind of feature and some kind of label, and it building a model that understands that and is then able to extrapolate it to kind of unknown areas where we don't necessarily have, that understanding.
Yeah, I was going to think get a bit more into the details, really get nerdy here. Neural networks is more where I'm going because there's different types, right? We're not all machine learning is the same, built the same way.
Yeah, for sure. So we're using a neural network in this paper, and a neural network is based on the architecture of a human brain, essentially. So it has various kind of neural nodes and connections between those nodes, and is assembling a kind of unquantifiable knowledge of those relationships in a different way to the way that like a regression is a machine learning method, but that's learning a very like simple linear relationship between things. This is a very complex, non-linear, like very hard to even sort of picture in your head really what a neural network looks like. It's kind of beyond visualization, and that kind of gets to how advanced these methods are.
Complete aside, you said it's a lot like the brain. Do the two fields actually kind of intersect there a little bit?
What do you mean? Like, are we programming human beings here?
Are we actually taking what we understand of a brain and actually utilizing that information to create a neural network?
Yeah, in a way, you can kind of look at it in that we're sort of creating a artificial geologist in a lot of ways, a geologist that is able to look at data and kind of use their own understanding of the connections between the data and then make predictions based on what it sees. Obviously, it's a bit more complicated than that, and we don't want to replace our geologist friends. We're always going to need their inputs, and these things are being built as tools for geologists. But it is essentially a brain that we're creating here.
Yeah, I guess it takes a geologist to understand the output.
Yeah.
You're never going to replace the geologist because they have to feed it, and then they have to understand the output.
Absolutely, yeah.
I guess that gets to the next part of the question. Like AI machine learning, it's revolutionizing some aspects. In some cases, it's more instead of revolutionizing something, it's like methods in marketing. Like I guess this happens every time there's a new technological disruptor that's out there. But this is peer-reviewed. It's solid science backing with real-world results. What's the strategy to break through the noise around AI and deliver real results and get people to believe in it? I mean, it's not really to believe in it, but to understand the results and how they can use it. There's just so much out there right now.
I wish I knew the best strategy, Jeff. I think our strategy is to just kind of be as honest, like scientifically honest as possible about the capabilities of this and also the limitations. I think a lot of those kind of hype companies don't discuss the limitations, and that's what makes it snake oil in my belief. I think what we're doing by regularly publishing and talking about what we do is building that trust and acknowledging the inherent faults of all AI is kind of allows us to actually work around those faults in a smart way by integrating as much input and knowledge from geologists and field experts to kind of build that tool rather than the sort of vague black box that I think has a lot of pitfalls in our industry. Okay,
so let's pivot back to the results. So this is an evolving tool to find mineral deposits, but what did you find going through this study? What was anything new and surprising that we can discuss here?
Yeah, I mean, it's there's nothing particularly revolutionary about what we did. It's more kind of how we framed the problem, I guess. in terms of where this will be going in future, I think the holy grail is to integrate that kind of 3D information. This is a very, very 2D problem, and I think we want to. It's one thing like predicting where to drill on a map, but actually like how deep to drill is kind of the holy grail in my opinion. So I think the kind of evolving steps are to look into hybrid approaches that kind of combine the advantages of neural networks and AI with traditional geophysical inversions and 3D interpolations as well. And I think we hope to be able to talk about that in the near future.
Yeah, I guess we didn't even touch on the fact that this is really providing a 2D map, right? Like the idea is you're providing a heat map or something like a heat map that you get warmer colors when you're closer to what you're looking for. In this case was gold, right?
Yes, exactly, yeah.
So I guess the obvious question is, why can't we do it in 3D? Like what's the limitation?
I think that there is a computational limitation. I think it's also just the kind of how you frame the problem. I think this is a very unconstrained kind of solution that we've developed. I think a 3D solution, because it's in so much more resolution and there's so much more information, I think you have to introduce a lot of constraints to that in a positive way. I think that's a good thing to produce models which are consistent with with your actual 3D information. You just have to parameterize that a little bit differently. And it's not something which is unachievable and is something that we are working on.
So you would say it's more a function of not having 3D data? Like we have some, but again, being a geophysicist, and we've covered inversions before, inversions are non-unique. So it's you can use them, but you can't use them for like your labels, right?
Yeah, exactly. It's an inversion is a subjective interpretation of objective data, and that's where the non-uniqueness comes from. And you can there's an infinite amount of models which satisfy a given data set, and we do things in inversion to try and reduce the amount of models which do satisfy that data set. But the more you can constrain and limit that process, the better.
So I guess more to the frame, like I'm familiar with geophysics and inversion models, and I guess I'm familiar with geologic models, but generally speaking, there isn't that many geologic models out there to be had that aren't similar to inversion models, that they're just interpolated between. We don't have a lot of labels. So is part of the reason why we can't have these 3D prospectivity more to the fact that we just don't have 3D data? Like how do you bring a DEM into depth, or things that you collect on the Earth's surface, into something you can actually get at depth? The only thing I can think of we have is the drill holes.
Yeah. And drill holes are obviously incredibly valuable. That they're expensive, but that's an objective observation of what the lithology it actually looks like, and you often get geophysical information with that too. So I think the real value comes from combining that knowledge of lithology, knowledge of downhole geophysics, and then combining that with surface geophysics. And kind of building something that satisfies all of those at the same time. And it's a slightly different problem to the one we tackled in this paper. This paper was more about a kind of rapid 2D kind of de-risking product. It's not supposed to be an objective or an accurate model of the subsurface. It's supposed to be something for simple de-risking and for exploration targeting. I think what the next step is this kind of 3D modeling, which builds a slightly more targetable model in terms of drilling.
Yeah, and actually, there's a couple of ways I've also seen this used. You're probably aware of them as well. Like in British Columbia, they sent out a request for proposals from companies such as ours. We didn't take them up on this, to figure out where places were prospective, so that way they could make decisions based on parks and I guess First Nations rights and stuff like that, and where to start that initial conversations. Are there other examples where it's being used to inform policy instead of directly trying to find the next deposit?
No, mostly people are quite distrustful of this. I feel like it's that there's a few like national efforts to do mineral prospectivity. Generally, they're quite simplistic, and I don't quite know the use cases for them. I think I think generally the main driver is coming from industry, from mines and from that kind of brownfield, which means on mine site kind of targeting.
So you're saying perhaps most of the real case, world case examples are locked behind data vaults that never get published.
Exactly, yeah.
What about other things that this same technology can be used for? Like, they can't be just for finding minerals. There's got to be water resources, identifying things on the Earth's surface.
Yeah. We never like reinvented the wheel with this technique. We produced a novel approach to it, but the actual technique is very grounded in decades of research. So this is a common thing in neuroscience and in medical sciences. It's the same technology that you would use to detect brain tumors, for example. You would train the model to detect the causative link between MRI images and brain tumors. And we actually started this study with a proof of concept using this malarial prevention data set, which was satellite imagery or aerial imagery, of water tanks in Central America, and for the purpose of mapping the locations where mosquitoes might breed. And that was kind of our proof of concept, was identifying water tanks in aerial data. So this is a very kind of a known technique, and the novel thing is just kind of how we framed that problem.
So we just went from mineral prospectivity to medical imaging to finding where mosquitoes breed to help control malaria, all in the same sentence.
yeah, a bit of a roller coaster.
No, but I mean that just shows like how wide this data or this technique or general science behind the technique can be used for, right? Like this is going to have real world implications.
Yeah, absolutely, and I think it will change the world of mineral exploration eventually. I don't know if it's quite there yet, but it's something that will only grow over time.
So before we go to the traditional last question, all things being equal, is there anything else you want to share science-wise? A future trip, a paper, a documentary suggestion? I don't know, is there a new Spinosaurus documentary coming out?
I don't know, that would be cool. I did, I mentioned the Spinosaurus paper earlier. I recommend checking that out. I don't know, my latest extracurricular obsession has been something called Bioacoustics, which is studying the vocalizations of marine life, because I'm really into whale watching. And so I've been doing a lot of research into that, and I might be potentially getting involved in some research in bioacoustics in the future, which would be very exciting. But yeah, I think that's a really interesting emerging field, being able to track the location and movements of whales for conservation purposes, and for notifying ships of when there's whales in the area, that kind of thing.
Cool. Yeah, we had someone on to talk about birds at one point and being able to identify species, although not yet individuals, from recordings just out in the trees. So that's cool. Is that like a citizen science thing, or?
Exactly. Yeah. There's a couple different citizen science organizations that work on that, and again, it's using neural networks like we have in this study to identify what whale vocalizations look like, and it requires that kind of building of the training data for the predictive models.
Is there any group or anyone that might be listening in the Vancouver area that they should get in contact with if they want to join this citizen science outreach?
Yeah, there's a really cool organization based in Washington called Orca Sound, and they're the main citizen science people working on predictive models. And then there's a couple more. The rest are kind of tied to universities. So there's a research team at SFU called Hallo, and then there's also some guys at UBC and UVic as well, all kind of working. But they all kind of work together. It's all a very collaborative approach. So I think Orca Hello.
The way science should be.
Yes, exactly. I think Orca Hello is the main citizen science kind of approach.
All right. Now, for the traditional, last, infamous question. What is your favorite science joke?
Yeah, I've got one for your long-time listeners that ties into my the paper I mentioned earlier. So my joke is a Spinosaurus walks into a bar. The bartender asks him, "Why the long sail?" The Spinosaurus says, "I have absolutely no idea." And the joke is that we have no idea what Spinosaurus
What it used to sail
what
for.
it did. Yeah,
I got it now.
Yeah. It takes a minute.
Oh boy. Normally I get it right away, or I feign polite indifference. This time I was like, no, I'm going to ask because I really need to know. Okay, well, thank you so much for being on.
Yeah, thanks, Jeff. It was a pleasure to be on, and I'd love to come back sometime.
Fantastic, but you'll need a new joke.
Yes, one that works immediately this time.
Well, that brings another episode to a close. Thanks for joining so far. Remember, send some feedback via the email in the show notes. Reach out on social media. Make sure you've subscribed to the show so you don't miss an episode. And give the gift of science. Tell a friend. And I'll see you in 2 weeks.
In a world so chaotic, so misbehaved, echoes of melodies remind us it's all waves. Colors weave stories painting the sky, swaying to rhythms as the galaxies fly by. Her